Okay, so welcome back. Now in this video, we are going to do an equipment test. We are going to use our Arduino Nano, and we talked about in previous videos how to set it up to do data acquisition and logging. And we're going to use that capability now to test a piece of equipment. And the piece of equipment we're going to test is this power supply. And this is basically an ATX power supply that I took out of a computer and modified. You can see I put a project box on the front just to bring the 12 volt, 5 volt, and 3 volts out. And I put a meter, voltage and current meter, and a couple switches just to make it accessible. But really, it's just a 460 watt ATX power supply, a Dell power supply. Now, in a previous set of videos, we went into some depth in a series called Debunking Computer Myths. We went into some depth to understand how these ATX power supplies work internally in order to debunk some of the myths. And one of the myths was that ATX power supplies are junk. If you overload them or short circuit them, they're going to go into a ball of flames and burn down your house, and you should never use them on your bench. So we went through and we looked at the internals, how this works. We looked at the internal supervisor circuit that's designed to shut these down before the currents get too high and so on. So I encourage you to take a look at that series. We went into some depth in how these work. And what we did as part of that is we used a lab jack and we did a test where we actually applied an overload and short circuit to this to see if it would actually protect itself and shut down before the currents got too high. And we're going to do that same thing now, and we're going to use our Arduino Nano as a data acquisition device and perform the same test. We're going to take the 12 volts output of this ATX power supply and apply an overcurrent. We're going to apply a rheostat across it, a variable resistor, and I just did a video recently about what is a rheostat. And basically it's going to be a variable load, and we're going to go from an overload to a short circuit across this 12 volt terminal and see what happens to this. Does it protect itself, or does it go into a ball of flames and burn down the house? So what we're going to do is I've got here a few components. Let me explain them. So I'm taking the 12 volts to ground out of one of the rails of this power supply. It's got 3 rails, 3 sources of 12 volts. And I'm running that into this resistor, a variable resistor that goes from 5 ohms down to 0. So if this is 12 volts and you've got 5 ohms, you can expect that it's going to start out at a couple amps, 2 or 3 amps. And then as I decrease this, the load current on this power supply is going to increase, and when this gets to 0, it's going to basically be a short circuit, and we're going to see what happens to this power supply. Now I'm also feeding from the plus 12 volts into the resistor, and then it comes out of the resistor to this terminal block, and the connection goes into this device, and this basically converts the DC current coming into these terminals into a corresponding output voltage that goes from 2.5 to 4.5 volts DC as you vary this current from 0 to 20 amps. Okay, so we should see a variable voltage related to how much current is flowing. And I'm going to feed that into an analog input of the Arduino Nano so we can measure it, and we can grab the data using our logger application we developed and plot it to see what the actual results were. Also, I did a video on how to use the serial monitor to grab data and plot it as a CSV. So either way, but we can still plot a chart to show what the response is. So I'm also measuring on one of the channels of the scope the voltage going into this Arduino Nano, and we can expect that as we decrease this resistance, it's going to go up, and hopefully at a certain point, when it gets down towards 0, it's going to shut down. So what I'm going to do first is I have this set at 5 ohms, And I'm going to turn this on, and I'm in roll mode. You slowly see the log data, and you can see it went up to about 2 amps. And that corresponds to a little over 2.5 volts coming out of this device and going into the Nano. So what I'm going to do is I'm going to decrease the resistance, and this voltage should go up, and keep a watch on this power supply, because hopefully when it gets up to its rating, it's going to shut down and everything's going to shut off. So now I'm set at, so you can see it, 2.1 amps, and you can see this is flat. And I'm going to increase this, and you can see I'm decreasing about to 4 ohms. It's going up to 3 amps, and you can see this plot is increasing. And I'm up at 5 amps, I'm up at 6 amps, and now I'm going to go down, and suddenly it shuts off. Okay, so you can see the power supply automatically shut off, and you can see it went up to a certain value, and then the output from this current sensor went to 0, which means this thing shut down internally. And now what we can do is we can take a look and see what's the rating, when is it supposed to shut down, and what did it actually shut down at. Okay, so now I've gathered that data that I grabbed from the oscilloscope, and we grabbed it as a CSV chart. And again, I showed in recent videos how to do that with a Arduino Nano. You can either use the serial monitor and monitor the current and copy and paste it into Excel, or you can use the C# application we used. But basically, this is the results. Now, let me show you how I went through and got it. These A and B columns are the raw data coming out of the current sensor into the Arduino Nano. And you can see I've got about 1/10 of a second in between data gathering. So it's 0.1, 0.2, 0.3. So every 1/10 of a second it's gathering data. And the values are over here, and that's the raw data. Now notice that at 0, when there was no current flowing through the device, I got an output of 2.5 volts, okay? And 2.5 volts is what this current sensor puts out with no current flowing in. It's kind of the base value. So all of these values are relative to a 0 value of 2.5 volts. So what I did is I made a new column of data, and I subtracted out that 0 value of 2.5 volts, and to get closer to the actual current value. All right. So if 2.5 volts is 0, then that means that we start out with 0 volts. But also we need to take into account that for every 1 amp that flows through that sensor on the primary, we get a 0.1 volt increase. So there's 0.1 volt for every amp. So what I had to do is I took this value, this B2 value, for each of these time steps, subtracted out this initial value, and then divided that by 0.1, since there's 0.1 volt per amp. And the result is this column right here that shows the actual value in amps that we can plot. So I plotted the time versus the actual amps, and here is the result. Okay, you can see time in seconds, so I get basically no current. That's this area right here. I get no current up to about 7 seconds, and then I apply the 5 ohm resistance, which means about 2.5 amps, and you can see here I am 1 amp, 2 amps, a little bit over 2 amps, and then I start to decrease the resistance, which means increase the load, and you can see the amps in DC. I got 5 amps, 10 amps, 15, and it goes up and up and up, and it finally goes up to 15, 16, 17, a little over 18 amps, and immediately shuts down and then goes back to 0. And we saw that when we did the test, the lights on the power supply flicker and it went off. So now we need to say, well, was that correct? It went up to 18 amps and shut off. Was that correct? Let's look at the nameplate and see what the ratings are. Now, let me increase this so you can see it. This is a Dell switching power supply, maximum power 460 watts. And you can see if you look down here, here are the ratings of the different rails. I've got a 12 volt A rail, a 12 volt B, 12 volt C, and then, so I've got three 12 volt rails. I've got a 5 volt, a 3.3 volt, and a minus 12 and a minus or plus 5 auxiliary. So we applied the short circuit across this 12 volt A rail, and it says the rating is 18 amps. Huh. So it looks like, even if it was across this B, it looks like this power supply shut off right at or above its rated current. So it turns out, as we talked in the previous videos on debunking computer myths, that this power supply has an internal integrated circuit. All ATX power supplies are supposed to have internal protection. So unless you get a piece of junk, it's got this internal protection that senses the current and automatically shuts it down above its rated current. And you can see it actually did that in this for this power supply at 18 amps. So the point here is that first of all, it's really good to answer questions not by looking on the internet and believing people who don't really know the answer, but to actually do the test yourself. And also the point here is that you can use like an Arduino Nano to do really good and useful data acquisition stuff. And you can get some good data rather than just spending your time lighting LEDs. You can actually test stuff. Now, that being said, do not do this at home unless you're qualified, okay? If you have a piece of junk power supply or a not working power supply, you can get a problem with these currents. So be very careful. But the point here is just to say that, you know, these power supplies, if they're an ATX power supply, they are required to have internal protection. And as long as that's working, you should be fine. But again, it is a very risky thing to do tests like this on equipment. So don't do it yourself unless you're qualified and you're willing to take any risks associated with it. So anyway, I hope that helps. Take care and have a really good day. Thanks.